Good evening, all of you. Welcome to the fourth day of Series 3 short-term training program sponsored by AICTE, held at Roland Institute of Pharmaceutical Sciences. Today we have with us Professor Sukant Tripathi sir, Professor Barampur University, very renowned and eminent professor. I welcome on behalf of Roland Institute of Pharmaceutical Sciences, Professor Sukant Tripathi sir to this short-term training program, and I hope SAR's lecture will definitely benefit all the participants. So before SAR starts his presentation, I request Dr. Gautam Kumar Jana to introduce Professor Sukant Tripathi sir to the audience.
Thank you, sir. Good evening, everyone. I, Dr. Gautam Kumar Jana, Associate Professor, Roland Institute of Pharmaceutical Sciences. It is a privilege to introduce Dr. Sukant Tripathi sir, the speaker of the third session of STTP. Dr. Sukant Kumar Tripathi was currently working Professor of Physics and Dean of Faculty of Science and Technology, Barampur University, Odisha. Dr. Sukant Kumar Tripathi did his PhD in Physics under the guidance of Professor Anand Rao of NIT Jamshedpur. He has guided 8 doctoral and 12 MTech MPhil students and had published about 50 publications to his credit. He visited the University of Electrocommunication, Japan, Brunel University, London, and Institute of Atomic and Molecular Sciences, Taiwan, Center for Condensed Matter Sciences, NTU, Taiwan, as visiting scientist on collaborative research. He has authored one book on material science and engineering. Currently, he is the coordinator of the Center of Excellence of Nanoscience and Technology for the development of sensor, a 3 crore project sanctioned by the OHEPEE, Government of Odisha. He is coordinating the DST FIST program to set up the Center of Applied Photonics to develop experimental facilities for the fabrication and characterization of the third generation solar cell. Dr. Tripathi is a life member of the Photonic Society of India, Optical Society of India, Indian Society of Technical Education, a patron member of Odisha Physical Society, and a member of IEEE Photonic Society. His current research interest includes nanophotonics, optical sensors, and solar cell. His current research interest includes he is a regular reviewer of IEEE Photonics Journal of Applied Physics, Chinese Optics Letter, Taylor and Francis, and Optical Fiber Technology Elsevier. He is a governing council member and an academic council member of Institute of Physics, Bhubaneswar, and executive council member of Odisha Vigyan Academy. With this brief introduction, I request Tripathi sir to address the gathering virtually.
Okay, thank you, Dr. Jenna, for a nice introduction. So the screen is visible?
Yes, sir. Yes. Yes, sir. Visible.
Okay. So I should first thank the organizer for inviting me for a talk. The talk, as you can see in the screen, is biosensor design using surface plasmon resonance. Basically, I am from the Department of Physics, and when Niranjan invited me for this, FDP, I thought that I should plan something which will be closely related to this biology also. In fact, in the last 2 years, I have started working in some biological sensors, which I will also present in this presentation. So this is my center. In fact, this is the Center of Excellence in Nanoscience and Technology for the Development of Sensor. In fact, this center has started since the last 1 year, which is funded by this Department of Higher Education. This is a 3 crores project. And the project is basically to design prototype of sensors in the area of healthcare, environment, and food security. So I thought that I should speak something related to this biosensor design. So I have planned my talk accordingly. In fact, I will try my best to avoid the detailed physics, but I will try to explain the basic physics. And since the participant, I think, are the teachers from different pharmacy colleges, so I assume that they have a background of +2 science physics. So therefore, my talk will be restricted to that. I will not go beyond that +2 physics, and I will try to explain the concept of the biosensor design, assuming that the participants have a knowledge in +2 physics. So this is my plan of my talk. First of all, I will talk something about surface plasmon resonance, based on which we have attempted to design these sensors. And on this SPR, there may be some subcategories this is called as the local surface plasmon resonance, in short LSPR, and this is long range surface plasmon resonance, in short called as LRSPR. So these terms I will also explain in brief. And once I will complete this basics of SPR, LSPR, and LRSPR, I will try to explain how this phenomena can be realized in some prism configuration and optical fiber configurations. Now, once you have completed this, design or the principle of SPR, LSPR, LRSPR in some prism and optical fiber configuration, you will immediately try to understand how this biosensor design is possible by using this SPR, LSPR, and LRSPR. Now, in the last 2 years, in fact, we have attempted to design some sensors, sensor to measure albumin, sensor to measure glucose level, and sensor to measure some other biological parameters. And this is the reason why I have thought to mention all these applications in this presentation. First, I will explain how this SPR, not SPR, in fact, strictly speaking, this is LRSPR, can be utilized for the glucose monitoring. In fact, this is non-invasive glucose monitoring. And then you will see how this LSPR, local surface plasmon resonance, can be used to detect albumin. And finally, we will also see some nanocomposite coating based sensors for this refractive index sensing, because as you will see, once you can detect the variation of refractive index, you can design any biosensor of your choice. And of course, finally, we will give some conclusion at the end. Okay, so this is in fact the basics of this surface plasmon. So let me take some time to explain what is this surface plasmon resonance. So I am not using any mathematics intentionally. You can also use some mathematics to explain this phenomenon, but let me explain in a very layman language. Now let us say this is a metal, right? Now if you have a metal and if you send a light into this metal, then there may be a possibility of oscillations of these electrons. And in fact, the collective oscillation of electrons may take place inside this metal. As you know, if you have an insulator, there is a less number of free electrons, so there is no possibility of oscillation of electrons. But if you take metals like copper, for example, and if you will give some external disturbance, for example, electric field, then the free electrons will move to form electric current. Similarly, if you will take a metal and it will send light instead of this electric field or potential difference, there is a possibility that the electrons which are there inside this metal will oscillate collectively. And this collective motion of electron is called as the plasmon. In fact, this collective oscillation of electrons will give rise to a wave inside this metal, and this actually is called as a plasmonic wave. So this plasmonic wave is possible if you can send light into a metal. So this is called as the bulk plasmon because the plasmon is formed inside this metal. So this bulk plasmon is of no use for our application. What is used in our application is surface plasmon. Now, when the surface plasmon will take place, if you will take the same light and you will introduce into this metal, under certain condition, the collective oscillation of electrons will take place on the metal surface instead of in the interior of this metal. And if this is the case, then this is called the surface plasmon. And this wave which is formed here due to this collective oscillation of electron is called as the surface plasmon wave. Now, I have explained this bulk plasmon which is not used in our application. Then I have explained surface plasmon which is produced on the surface of a metal. And the third type of plasmon is called as local surface plasmon. Now, unlike this surface plasmon where this wave is confined to this total metal surface, in case of local surface plasmon, the plasmon is restricted to a particular location. It will not cover the total metal geometry. It will in fact be restricted on a particular location of this metal. So similarly, when you will shine light here to this, to this metal particles, then this metal particles will also oscillate, okay, and they will form what is called the surface plasmon or localized surface plasmon. Here, as you can see, this plasmon is traveling in this metal surface, so it is restricted from here to here, whereas here this surface plasmon is restricted to a particular location, and therefore this is called the local surface plasmon. Local surface plasmon can be also used to design these sensors. Now, this next type of plasmon is called as the long-range surface plasmon resonance. Now, when this long-range surface plasmon resonance will take place, see here, if you ask me how we will realize this surface plasmon resonance, the surface plasmon resonance can be realized if you will coat a thin layer of metal like silver and gold on an insulator. For example, you take glass and onto the top of this glass surface, you give a thin coating of either silver or gold. Then you will find the surface plasmon if you will excite this with a suitable light. Similarly, if you want to have this local surface plasmon, then you have to use some small particles, small metal nanoparticles like gold and silver. These are sometimes called as nanoparticles or sometimes also called as quantum dots. So if you will use some quantum dots on a insulator, instead of a metal surface coating, then you will use or you will get what is called the local surface plasmon resonance. Now, how this long range surface plasmon resonance is realized? In this case, you have to coat this insulator not only with the help of a thin layer of metal, but you have to enclose this metal with the help of two insulators. So this is the bottom insulator and this is the top insulator, and between these two insulator, this thin layer of metals like gold or silver is introduced. So if you coat a multi-layer structure like this on a glass surface again, then you will realize what is called as this long-range surface plasmon resonance. So I can use this different plasmon based on what coating you are giving onto a insulator like a glass or plastic. So if you will coat a thin layer of gold or silver, then you will get what is called as this surface plasmon. If you will coat quantum dots of gold or silver, then you will get local surface plasmon resonance. And if you will coat a multi-layer stack like this on a glass or plastic surface, then you will get long-range surface plasmon resonance. Then when to use this surface plasmon? In fact, I said this is surface plasmon, but the phenomenon which we'll use is not surface plasmon. This is called as surface plasmon resonance. And what is surface plasmon resonance? We will see it later, maybe in the next slide. But before that, let me tell you that this surface plasmon wave which is produced in this surface will in fact decay exponentially exterior to this surface. So what is the length scale up to which this field will decay? Of the order of nanometer. That means the field which will escape out of this thin metal surface is of the order of 50 nanometer, 60 nanometer, or at best 100 nanometer. Whereas here also the same thing will happen in case of local surface plasmon resonance. The field will penetrate up to again 50 to 100 nanometer, but not more than that. Whereas in case of long range surface plasmon resonance, the field can penetrate up to micrometer. When I say micrometer, this is 1000 nanometer, and therefore this is called as the long range surface plasmon. So here in these two cases, this penetration is very small, penetration of field is very small, of the order of 50 nanometers or at best 100 nanometers. Whereas in case of long range surface plasmon resonance, this penetration is very high, of the order of 1 micrometer, and sometimes it is also 5 micrometer. Why this penetration of field is important? Because the realization of the sensor is due to the interaction of this field with the analyte, and the analyte will be coated onto the top of this layer of gold or silver or metal. So therefore, if your analyte dimension is very small, then of course you can use this surface plasmon or localized surface plasmon. But if the analyte, for example, I am using a bioentity like cell, the dimension is not nanometer, it is the order of micrometer. So I cannot use simply surface plasmon or local surface plasmon because it can only penetrate up to few nanometers. So therefore, if I want to detect or sense cell or bacteria, then you have to use long range surface plasmon resonance, where the penetration of field is maybe 1 micrometer or more than 1 micrometer. As I said, sometimes it is 5 micrometer. So therefore, depending on what is the bioentity which you are detecting, you have to selectively use either one of these phenomena, surface plasmon or local surface plasmon or your long range surface plasmon. Now, as I said, this bulk plasmon is not used in any applications. So I will explain, in fact, in my talk, one of the application of this local surface plasmon resonance and another application of long range surface plasmon resonance. Now I have explained somehow the surface plasmon, local surface plasmon, and long range surface plasmon. Now let us try to understand what is in fact this resonance, surface Plasmon resonance. I have said surface Plasmon. Now, what is surface Plasmon resonance? Now, resonance is a term which is used, in your standard +2 physics textbook. This resonance will take place when the frequency of the external frequency will be equal to this natural frequency of oscillation. Okay, so this is the standard definition of resonance. For example, you might have studied or you might have done an experiment in your +2 physics laboratory, like a tuning fork was there, and you are vibrating this tuning fork with the external frequency of, you are vibrating this wire with the external frequency of a tuning fork. So when the frequency of vibration of the wire, test wire, becomes equal to this frequency of the tuning fork, then there is a resonance and the wire will vibrate with maximum possible amplitude. So this definition of resonance remains the same. So if you want resonance, then the frequency of two should be same. Now, what are the two frequencies here which should be same so that you will get the resonance? Now, here is a diagram where I have explained this surface Plasmon resonance, the basic principle. This is in fact a basic glass prism, and I have coated a thin metal to this glass prism. So this is the prism here, and this is the thin metal. Okay. Now, here, as you can see, this prism, into this prism, I have put some light here. Okay. This is the light which I have incident into this metal, right? So that I can excite the plasmonic wave. Okay, so that means when you will shine light into this metal through this insulator, in fact, then there will be some plasmonic wave which will be produced, and this is surface Plasmon wave. Because these waves are produced throughout this metal surface, this is surface Plasmon wave. Now, as you know, a wave has a particular characteristic that is called the wave vector. And as you know, wave vector is related to this wavelength of that light, and k here is the wave vector, and it is related to this wavelength as 2 pi divided by lambda. Now, this k is the wave vector of the incident light, so that the wave vector which will go along this direction is kx. In fact, you can resolve this into two components, one along x direction and another along y axis. So this component of field along this metal surface is kx, and this component in fact will produce this surface Plasmon. In fact, this will excite this surface Plasmon, because surface Plasmon cannot be produced without any external disturbance. So the disturbance which is produced the surface Plasmon here is this incident light. And we should also remember here that this surface Plasmon wave cannot be formed if you will just shine light as you like. If you will shine light in a particular manner, okay, if this light incident is like a TM means electric field will oscillate along the direction of this metal surface, then only it can excite this surface Plasmon. Okay, so this is this kx, and kx is the surface Plasmon, the wave vector of this incident light wave. And once this incident light wave vector falls here, then this surface Plasmon wave is also produced, and this surface Plasmon wave has wave vector kxp, which is different from the incident light wave. So the incident light wave has wave vector kx, and the plasmonic wave which is produced has wave vector ksp. So in general, this kx and ksp may not be same. So even if kx and ksp are not same, then also there will be some plasmonic wave which will be produced in this metal surface. But when this kx and ksp becomes equal, when this wave vector of light to a signal and the wave vector of the plasmonic wave becomes equal, then there is a resonance of the surface Plasmon which will take place. I say that resonance for the resonance to take place, you should see that two frequencies or two wavelengths should be same. And here this wavelength or the frequency of the incident light should be same as the frequency or wavelength of this plasmonic wave which is produced. Now, what will happen when there is a plasmonic resonance? When there is a plasmonic resonance, you will see that the reflected light. So when you are putting the light here, then this is an interface, so the light will be reflected like this. So when there is no surface plasmon resonance, you will see that this light, considerable amount of light is reflected here. But as soon as this surface plasmon resonance is formed, when kx is equal to kxp, then you will see that there will be no reflected light or minimum reflected light. So the reflected light which was present when there was no surface plasmonic resonance will vanish when there is plasmonic resonance. And as you can see here, this is the condition which is required. What is this? This is in fact this value of kx. I have not mentioned, of course, this is actually kx, and this is the value of ksp. You can just find this relation by using standard electromagnetic wave equations, which I will not go into. And when this kx is equal to ksp, that means kx is here, ksp is here. When these two are equal, then there will be surface plasmon resonance. And when the surface plasmon resonance will take place, then you will see that there will be no light or minimum light which will come as the reflected light. Now, if you will see this relation, in fact, this omega is the angular frequency, c is the velocity of light, epsilon 0 is the dielectric constant of free space, and theta here is the angle of incidence of this light. This angle is your angle of incidence, theta. And epsilon 1 is here the dielectric constant of the surrounding. Epsilon 2 is the dielectric constant of this metal. If it is gold, this is the dielectric constant of gold. If it is silver, then dielectric constant of silver, something like that. So when this relation will satisfy, then you will get plasmon resonance. Okay, and when there is plasmon resonance, you will not get any light here. The light is something minimum. No reflected light or minimum reflected light will come here. Now, if you see this relation little carefully, then you can realize that there are two different cases where this resonance will take place. The first case, as I have mentioned here, if you will keep W or omega, not W, omega as constant. Suppose I will keep omega as constant. Then if you will vary this theta, angle of incidence, then for a particular value of theta, this relation will satisfy. Because essentially there are two variables. One is omega and another is theta. So either you can keep omega constant and vary theta so that this equation will satisfy, or you can keep theta constant and vary omega, then this relation will satisfy. So why you have to satisfy this relation? If you want surface plasmon resonance to take place, then you have to see that the relation should satisfy. Now, what is omega? Omega is something related to wavelength of the incident light. So omega is related to this wavelength of incident light, and theta is the angle of incidence of light. So in the first case of surface plasmon resonance, you keep this omega or wavelength constant and vary this value of theta. Then you will see that for a particular value of theta, there will be surface plasmon resonance. How will you know that there is surface plasmon resonance? You keep a detector here which will basically detect this light, and when there is a surface plasmon resonance for a particular value of theta, you will not find any light in the detector. Then you will see, then you will confirm that this surface plasmon will occur. Similarly, if you want surface plasmon by varying wavelength, then keep this angle of incidence of light constant and vary this wavelength of light source here, and then see or in the detector where you are getting this minimum light. So you will see that for a particular wavelength of light, there will be minimum light which will get at the detector. So this is how you can realize this surface plasmon resonance. Now, these graphs I have explained here, these two different types of surface plasmon. As you can see here, in the first case, I have kept angle of incidence of light constant and I have varied this wavelength. And this is reflectivity. I have measured reflectivity in the detector. Then as you can see, when you are varying this wavelength, for a particular wavelength, the reflectivity becomes minimum. That means what? For this particular wavelength, 752 or something like that, this surface plasmon resonance is taking place. and the dotted graph which I have changed here is due to the variation of refractive index in the surrounding. Why there is a variation of refractive index in the surrounding? Let me explain here that suppose I will put any medium here. Any medium means the medium or the analyte which I want to detect. For example, I want to detect a bioentity, then I have to put the bioentity here. Now, this surface plasmon resonance is very sensitive to the variation of refractive index of the bioentity or the variation of dielectric constant of the bioentity. Let me tell you here that refractive index and dielectric constant are related to one another. In fact, epsilon is root over of n is root over of epsilon. So they are related. So when you will put dielectric some bioentity here, depending on the change, a small change in the refractive index or dielectric constant of the bioentity, you will see that the reflected light, the minimum reflected light which was taking place without this bioentity is something different from the minimum value which you are getting without by the bioentity. For example, if you see this, for example, I have not surrounded this metal with some bioentity, you are getting this reflection minimum at this wavelength. Now, suppose I will surround this metal layer with some bioentity. Now, you see, you will not get this minimum reflectivity here, but you will get the minimum reflectivity here. So that means this shift in this minimum in the reflectivity or dip in the reflectivity is due to the bioentity which you have surrounded this metal surface. And if you will change this concentration of the bioentity, for example, I want to measure, let us say, albumin. Now, if you will change the concentration of albumin, then its refractive index will also change. So, if the refractive index, if the concentration is C1, then you will get one dip at a particular wavelength. If you will change the refractive index of this albumin to some C2, then this will also change, because as I said, the shifting of this reflectivity dip is very sensitive to the change in the refractive index of the bioentity which is surrounded by this metal surface. So this here in this case, what you are doing, you are realizing the SPR by keeping the angle of incidence constant by varying this wavelength. Whereas here, this is the second case where this wavelength of this light source is kept constant, but I have changed this angle of incidence of light, and this is how the reflectivity varies. As you can see, for a particular refractive index surrounding this metal, the reflective dip is here, and if this refractive index of the surrounding medium changes, then the reflectivity dip changes to this place. So this small change in the refractive index will give you a large shift in the reflected dip, and this is the basic principle of sensing using this surface plasmon resonance. Because even if this change in the refractive index is of the order of 0.001, then also there will be a shift in this reflected dip. So there is no other phenomenon where you can detect such a small difference in refractive index. Because as you will see, when you are changing the concentration of bioentity, there is a very small variation in the refractive index, and if there is no shift in this reflectivity, you cannot distinguish between two concentration of the bioentity. Therefore, SPR is a very accurate technique but to detect this bioentity. In fact, as you will see that how this refractive index change can take place for the variation of glucose concentration in the blood serum. Okay. Now, this is the experimental arrangement by which you can realize this surface plasmon resonance. As you can see, this is the light source, this is the detector where I can detect this reflected dip, where is no light is coming, the detector can do that. So this is the prism, this is the gold which is coated, and this is the sample cell. So for example, if I want to detect some bioentity, I have to put this bioentity inside, or I have to use a flow cell where this bioentity will circulate, and then this light will be illuminated. This is the light source, light will be illuminated to this, then this will come over here, and the reflected light will go here to this detector, and you can change this angle of incidence by rotating this, or you can change this wavelength by changing this knob here. So depending on the situation, you can see how this reflectivity dip changes with the change of this angle of incidence, or with the change of this wavelength of this light source. And in fact, this is a diagram to show you how this SPR can detect different refractive index. And in fact, you can see this is the refractive index, and this is the SPR angle per degree. That means how there is a change in the SPR angle with per degree. And if it is air, you are getting the point here. If it is water, it is here. If it is acetone, it is here. If it is ethanol, it is here. It is glycylmethane, it is here. So they're different. So this is the basic principle by which you can set off this SPR in the experimental arrangement. Okay, now let me also explain in brief how this biosensor design can be made out of this SPR principle. Now here, as you can see, this is again the prism configuration which I have explained, and this is in fact the gold layer, the thin metal film which I have coated, and this is in fact the surrounding. Now I said that if you will put some bioentity, now let me restrict my discussion to bioentity, not other material, because basically you are in the pharmaceutical background. So let us say this is a bioentity, any bioentity. Okay. Now I said that when you will change the concentration of bioentity, then there is a change in the, or there is a shift in the angle or wavelength in the reflectivity dip. But the question is, how we will ensure that the change in refractive index in the surrounding medium to this metal layer is due to the bioentity which we are going to measure? Can you give guarantee that there are no other bioentity which is present surrounding this metal, which will also influence the refractive index of the surrounding, and which will also give some contribution to the change in the dip of the reflectivity? So there is every possibility of that. For example, there is a X1 bioentity you want to detect. Unfortunately, there is X2 bioentity which is also present in the surrounding. So you want to detect X1 bioentity, not X2 bioentity. But the refractive index change which will take place in the environment will be due to X1 and X2. So therefore, the shift which is taking place here is due to X1 and X2 bioentity both. But how will you know, or how will you find the shift which is taking place here due to only X1 bioentity? For that, you have to make some arrangement like this. This is in fact called as antibody-antigen binding. So if you want to, for example, detect albumin, then you have to give an intermediate layer of antibody of albumin, which will attract albumin, not other bioentity which is present surrounding. So therefore, the change in refractive index which will take place in the environment to this metal surface is only due to this albumin, not due to the other bioentity which are present, because the other bioentity will not stick to this antibody. Only this albumin will stick into this antibody, and therefore the change in refractive index which will take place here is only due to the bioentity which you are interested to measure or detect. So this is what you have to do for biosensing application. You have to put a material which will bind, which will only attract the bioentity of your interest and will not attract other bioentity, so that there is a specific sensing mechanism. So this is what you have to do in the biosensor design. Now this is another configuration where you can realize this surface plasmon resonance. So far we have explained the prism configuration where you can realize this surface plasmon resonance. But there are also other configurations where you can realize this surface plasma resonance, and I have given here an other example like optical fiber, because I also work in this optical fiber. So here the principle remains same. You take a glass or plastic optical fiber and give a thin coating of gold or thin coating of gold quantum dot, or you give a multi-layer structure of insulator gold or insulator, then you can realize this surface plasma. For example, in this configuration, this is the optical fiber. In fact, optical fiber is a thin strand of glass or plastic where this light is allowed to propagate in a guided fashion. And here, if I can put some thin layer of gold or thin layer of silver, then this is your insulator, this is your metal. So therefore, there is a possibility of surface plasma. Similarly, you can see here, this is the fiber, this is the metal gold film, and you can realize this, surface plasma here. So just to give you a feeling that prism is not the only configuration where you can realize surface plasma resonance, but there are also some other configurations like optical fiber where you can realize this, surface plasma resonance. Okay. Now I think I have to wind up within another 20 minutes. I can do justice then. Okay, this is the first example which I thought to explain you. In fact, this is a design of non-invasive blood glucose sensor based on long-range surface plasma resonance. And this is like a thumb or finger touch sensor design. And you can see here the basic principle is something like this. There is a prism here, glass prism, and there is a multi-layered structure. You may ask here why you are putting a multi-layer structure. Why not a thin layer of gold, which will make this fabrication process much simpler. The reason for using a multi-layer structure is for the reason the field, as I say, the field which will decay exponentially is of the order of micrometer. If I will take a simple thin layer of gold, then this will actually decay completely after a few nanometer, 100 nanometers. Now, if you are pressing this finger here, finger tissue has different layers like epidermis, dermis, okay, and the blood vessels are present in the dermis. And if you try to see what is the total thickness of epidermis and dermis, this is nearly 2 millimeter. That means your decaying signal, SPR signal, surface plasma wave signal, should penetrate long distance so that it can penetrate into this dermis. Now, what is the basic principle of detection of glucose here? As I said, the glucose are present in the blood vessel in the dermis. So I will put some light and the light will enter into the dermis. And the light source which I have used here is a visible red light or visible red laser of wavelength 650 nanometer. So this light will go to this dermis layer, and in the dermis layer blood vessels are there, glucose is there in the blood, and this glucose will absorb this red light. And when this glucose will absorb this red light, then definitely the light which will receive at the detector will change. And the change in the detector input of the detector will be proportional to the absorption which is taking place due to the glucose level in the blood. And if you will see here, there is a table which I mentioned here. If you are changing this glucose level, there is a change in the refractive index. If it is 50 milligram per deciliter glucose, then the refractive index is 1.33876. If changes to 100, this is 1.35042, something like that. So if the glucose concentration in the blood changes like this, then the refractive index changes like this. And as I said, when the refractive index of the environment changes, then there is a change in the reflected dip. If we change the refractive index in the environment, then there is a change in the reflection dip, right? So you can see the difference. This is 1.338. This is 1.350. So this at 0.02, right? So that means when you are changing this glucose concentration by 50 milligram per deciliter, there is only a change in 0.02 refractive index unit. That means if your sensor is not that sensitive, it cannot detect the variation between 1.35 to 1.33. And this is why you need a very accurate sensor mechanism by which you can detect even small change in the refractive index. Now you can see this layer which I have used here. The layer which I have used, the multi-layer structure which I have used is silicon oxide, insulator, gold, silicon oxide. If you'll ask me what is the thickness of this total multi-layer structure, this is around 900. This is 400 silicon oxide, bottom is 420, this is 50, this is 400. So 420, 50, 470 plus 400, that is 870 nanometer. That means the total thickness of this layer is approximately 900 nanometer, and the light will go out to this 900 nanometer. And if you will use surface plasmon resonance, definitely this will not go beyond 100 nanometer. So light cannot reach to this, out of this multi-layer, thin coating. Now, once light reaches here, and since this is red light, it is found experimentally that red laser light can penetrate up to 5 millimeter very safely, very conveniently. And what is the distance you want to move into this finger tissue? Only 2 millimeter, because this dermis and epidermis combined thickness is 2 millimeter. So therefore, if you use red light and somehow red light comes out of this multi-layer structure, then it can easily move to this dermis layer where the blood vessels are there, and the blood vessel, the glucose in the blood will absorb this light according to this concentration of glucose, and therefore the detector output will change accordingly. And this is where we have seen how this reflected dip changes with this refractive index variation, or in other words, the refractive change in this glucose concentration. Then we found that there is a linear variation. If you are changing the refractive index, then the angle of incidence also changes accordingly. So you can indirectly say that x-axis is glucose level and y-axis is your angle, right? So this is what is called the calibration graph in our sensing mechanism. So once this calibration graph is over, then suppose I want to find the unknown glucose level, then just see what is the angle of incidence where you are getting this dip. Now suppose I do not know what is this glucose level. I just shine a red light and I found that this SPR dip is, of course, LR SPR dip is coming at 64 degree. That means what is the unknown glucose level? You just extrapolate like this. So this is the unknown glucose level. Sorry, unknown glucose level. Okay. So this is how you can calibrate this from this calibration. You can find this level of glucose from the calibration graph, and then you have to interface and directly read what is the glucose concentration. What is the beauty of this investigation? The beauty of the investigation is this is a non-invasive method to detect glucose level, and you should not prick this finger. Sometimes when you have to prick this finger many times, then it is not convenient. So this design will help you to measure this glucose level in a non-invasive manner, and because this is red laser light, and therefore it is also not dangerous to tissues. Okay, so this is how you can use this principle of long range surface plasmon resonance. And I have not used the surface plasmon resonance or local surface plasmon resonance, because for this application I need this light should penetrate through a longer distance of the order of few micrometer. This is why I have used this long range surface plasmon resonance. This is another application where we have also shown that I can detect albumin by using this local surface plasmon resonance. I have not used long range because for this application, if I want to measure albumin, then penetration of field up to few nanometer is sufficient, and therefore we thought to use this local surface plasmon resonance. Now, what you have to use for local surface plasmon resonance, you have to again create a metal dielectric interface. And as you can see here, this is a plastic optical fiber you have taken, and we have coated gold quantum dots. Okay, we have prepared gold quantum dots, and we have coated this with the gold quantum dots. So this becomes your plastic. This becomes your gold quantum dot. So the metal in dielectric interface. So therefore, there is a possibility of local surface plasmon resonance. In fact, there are some simulations we have made because at those time in our laboratory, there was only a single source 650 nanometer laser. So I cannot, as I said, if I want to see this surface plasmon resonance, then you have to vary this wavelength. Okay, so if you want to vary this wavelength, then you should have a tunable source where you can change this wavelength of the source. Unfortunately, when we published this paper in 2019, of course, 2018-19, we have only a single laser source of 650 nanometer, and therefore we have no liberty to change this wavelength of light source. So we have an expertise to prepare different size quantum dots, and we took this advantage of that. What you did is something like that. These are the gold quantum dots, and if you will change the size of this gold quantum dots, keeping this wavelength same, then also for a particular size of the gold quantum dots, you will get SPR. So SPR also depends on the size of this gold quantum dot. And because we have expertise in preparing different size gold quantum dots, we have made some initial simulation known as finite difference time domain simulation to see which size of gold quantum dot will suit for a 650 nanometer laser source. And as you can see here, it is found that from this simulation, it is found that 4 nanometer, if you can prepare a 4 nanometer quantum dot and coat here, then you can see that deep is coming around 650 nanometers. So we have prepared, we have synthesized gold quantum dot of size 4 nanometer. In fact, we prepared, made some characterizations, stem and all, and is found that the size is something 3.9 plus or minus 0.5 nanometer, and therefore we use those quantum dots and try to see whether you can sense this albumin or not. And this is how you have, this is the experimental arrangement, this is the source, this is the red light source, okay, and this is the detector, this is the fiber. Here these quantum dots are coated, and this is the taper region to take the light out, okay, and we have coated the antibody, then this antibody of your albumin, then this albumin different concentration, and then we see that there is a perfect straight line variation of this calibration. This is the BSA concentration, and this is the output of the detector. As you can see that there is a straight line behavior, so that you can use this as sensing application. One of the important property of the sensor or the characteristics of sensor is that the calibration plots should be linear. If it is not linear, you cannot use this for sensing application. So this is this calibration plots. For example, I put some unknown concentration of albumin, then suppose I find that this is 65 output, then I can find from the calibration what is the concentration of albumin. Here this is 0.0 something like that. Albumin is of course a very important material to be detected, because it is the variation of concentration of albumin resulted in some heart problem, in fact, and you might be knowing better than me. So we have used this albumin detection by using this phenomenon of what is called the local surface plasmon resonance. So one, I have used long range surface plasmon resonance for glucose detection, and another I have used local surface plasmon resonance for albumin detection. Now, there is also another, sensor design where we have also worked recently, and there actually what we did is something like this, because in the previous, design, we have to taper this optical fiber. You can see here, this is the homemade experimental arrangement where I can taper this optical fiber. Means the a small portion of this optical fiber has to be decreased in its dimension by heat and pull mechanism, and then you have to coat this. Okay, now when you will taper this fiber, definitely the mechanical strength of this fiber will decrease, and there is every possibility that the fiber will break, and therefore this mechanical strength of the sensor is an issue. To get rid of this problem, what we did recently, we have synthesized a new magnetic material. The material is mentioned here. This is iron oxide, barium molybdenum oxide disposed with urium. So europium disposed core cell magnetic nanoparticles. If you will coat this material on simply a clad, that means the inner part, you don't taper this fiber as I have done previously. Simply take the clad and coat this, this material. Then you will see that this field will come out as strong as in case of tapered optical fiber. In fact, this is the design which we made. This is the source, this is the detector, and this is the flow cell where this bioentity will be circulated for the detection. Okay, and what you did here is this is the portion where this magnetic nanoparticles are coated, and when you will flow this, when you will introduce this bioentity here, okay, and it will detect, and once this concentration C1 is over, just you take out this and put another concentration bioentity. So change the concentration, then see what is the output you are getting at the detector, then plot a calibration plot from which you can find the concentration of the bioentity. So this is of course not something related to SPR or LSPR or long range SPR, but this is something related to the sensor, biosensor design, where now you are trying to use this sensor. In fact, I have used this sensor. We have used this sensor for the refractive index sensing, and now you are trying to use this for sensing some biological parameters. So maybe I don't know what we will do or what will be the successful result. We are trying for malaria now with the help of geology department. So let us see which bioentity will be helpful for this design. Based on that, we will propose that this design also can be used for a biosensor design. So I think my time is over, or 2 minutes there. Okay. To end my lecture, I should thank the organization which have funded me. First of all, I want to acknowledge this Department of Higher Education for funding the Center of Excellence for Nanoscience and Technology for development of sensor. And also I should thank this DST FIST for sanctioning nearly 1 crore for developing another lab. And of course, this funding is from World Bank, in fact. I should acknowledge them because whatever I am doing is only due to their financial support. Lastly but not least, I should rather acknowledge my PhD students, due to whom I am able to present before you. Because whatever I am doing or I am presenting is the result what they have made maybe in the last 2 years or so. So thank you very much again for giving me an opportunity to share some of my work before you. Thank you very much.
Thank you very much, sir, for your presentation on a topic which is very much related to our theme, that is integrating research in basic science with applied pharmaceutical sciences. Really, sir, you are doing a great work. I think
Thank you.
especially that non-invasive device for the estimation of glucose will be a great help to the patients because they are pricking their fingers every day. Sir, there are few questions. Just I
Yeah,
am quick
sure,
on
sure,
that. It
sure,
will
sure,
appear.
sure, 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 sure.
Can you see the question, sir?
Just 1 minute.
Sir, you minimize your PPT.
Yeah, yeah, sure. Okay, so the question which I can see is how to prepare quantum dots in nanorans, right? Yeah.
Sir.
See, we are preparing quantum dots by a simple chemical approach. This is called as bottom-up approach. Actually, there are two different ways by which you can prepare the quantum dots. Either you go from this smaller size and you get the bigger size, or take the bigger size and divide till you will get this nano size. But you are doing this chemical method. In fact, you are taking the chemical route to prepare this quantum dots. This is what is called as the bottom up approach. So we use some chemicals, in fact, to prepare this quantum dots. In fact, this is not only the quantum dots which we have prepared in my lab. We have prepared maybe 15 or so quantum dots, like gold quantum dots, silver quantum dots, PBS quantum dot, as I've shown, magnetic quantum dots, okay, and CDSE, CDS. So many quantum dots can be prepared, and the process is very simple. For example, I want to prepare gold quantum dot. Simply you have to take gold chloride and you have to use a reducing agent to reduce it. Of course, the other parameters are there which you have to optimize. So to briefly explain, this is a chemical method by which you are preparing the quantum dots. I think it can make some sense, right?
Yes, sir.
Is there any non-invasive device available in the market for estimation of glucose? Yes, yes. Market non-invasive devices are there for glucose detection, but all these devices which are available till today are based on infrared technology. That means you are using a infrared source, right? I have shown that I am using red light. Infrared source has some disadvantages. The first disadvantage is that infrared light cannot absorb this glucose properly. This is why, though the devices are available in the market, but the error is more actually. So therefore, the market is not success. So this is why you have, in fact, these prototypes are already available for infrared non-invasive sensors. So just to get rid of that, because to minimize this error, we thought we should go for red light. So what is the advantage of red light? It is found that red light can absorb this glucose very large amount. In fact, the red color light of red laser has a property that it will absorb this glucose to a larger extent. And as you can see that when this glucose concentration is changing, the refractive index is also changing. And the refractive index variation is very, very small. In fact, you are detecting the refractive index variation in our detector. Of course, the change is glucose level. But due to this change in glucose level, what is changing really is the dielectric constant or the refractive index. Now, if you will use infrared, because infrared will not absorb this, glucose will not absorb this infrared, the difference in this glucose range, for example, I have said 0.02. So when it is going from 50 to 100 in glucose level, it is difference of refractive index of 0.02. But if you use infrared, this will be 0.00 something. Therefore, you need some more accurate instrument than this. And this is the reason why this non-invasive device actually failed. because when the accuracy becomes very, very small, there is every result that your detector is not that sensitive to detect that small variation. But here it is 10 order less than that, 0.00 something, here 0.0 something. So therefore there is a 10th order variation. Therefore this detection is much more accurate than the infrared based sensor design. And to answer your question, yes, it is available, but it is based on infrared sensor. And recently, I don't know whether you have, this is not using light. In fact, this is using SET. They designed recently, maybe 1 month back, one group in maybe Japan or German, I have not remembered exactly. They have actually designed a non-invasive, of course they gave the prototype from the swept, not any laser light, swept. So you have to just put your swept on the device so that it will measure your glucose concentration. But again, that is the issue, because suppose you will measure this in a AC room, maybe you will not get the swept, and you have to wait for a long time till you will get the swept, then you will press this finger. So in this situation, I think this method, because whenever you like, you can produce this laser light, only you have to press this fingertip. You don't want any swept of your finger. So this is how you can relate merits of this sensor design.
Sir, one
Any
more question.
safety issues with radar? No, no safety issue, because say 650 is a visible laser light. So this is what I said also. 650 nanometer is simply a red laser, and the light power which I'm using is 3 milliwatt. So it is not dangerous. You can safely use this for maybe because here it will go into your finger tissue. So it will go for a fraction of second, in fact. Even if you will put this for maybe 1 minute, nothing will happen, in fact. So in our case, it will go up to a fraction, maybe 1 second or 2 seconds, because it will go and will reflected back. That's all. So there is no safety, I mean, dangerous to this radiation.
So thank you
Any
very much,
other?
sir.
Okay.
No, sir. No. So thank you very much, sir, for your presentation. And as I am your student, so I am really thankful that you have accepted our invitation. When I sent email, within 2 minutes you have replied. So really, I am thankful to you,
Thank
sir,
you.
for your
Thank you.
blessings.
Actually,
And I am looking for.
you people actually become happy to give some talks, but we become more happy when our student actually invite for a talk. So this is why immediately I send the reply that I am ready to, to take this, lecture. And you can also visit my lab sometimes, because we have developed a lot, in fact, in our lab. In fact, another thing which I have not discussed here, we are also doing the glucose detection, not glucose, HbA1c detection by using holographic microscopy. And we have developed that microscopy in my center with the help of the BARC Visakhapatnam, Babatunga Research Center. And now we are trying that also with the help of MKCG Medical College Pathology Department, Dr. Bar. So this is also another facility related to your area. We are trying to do that with a low cost solution for measurement of HbA1c. So sometimes Niranjan come to my lab and visit when the situation
Yes,
becomes
sir.
normal.
Sir, please accept this certificate on behalf of Roland Institute of Pharmaceutical
Yeah,
Sciences.
thank you very much. I accept this.
Thank you, sir. So in future also we'll need your cooperation, sir.
Yeah, definitely. Most welcome.
So dear participants, today's session is coming to an end. Tomorrow again you please join by 11 o'clock. Thank you, sir.
Okay, thank you. So
Okay, sir. You may log out, sir.